Alright guys, so I'm gonna tell you about the ESR method today. The ESR method, which is also called the EPR method, the electronic paramagnetic resonance or electronic spin resonance. So for ESR or EPR method, we need an unpaired electron or an atom with an unpaired electron. So that is a paramagnetic substance. First we need an paramagnetic substance. So the unpaired electron, which is either will have a plus up spin or a minus up spin, so that will interact with the external electric field. First of all, if electron intrinsically has spin, so it has some magnetic moment, so that magnetic moment will interact with an external magnetic field, which is H naught. If I put a paramagnetic substance in this magnetic field, suppose this magnetic field is along z direction, and if we put H naught field, if we put that electron or the substance in H naught field, so from Zeeman effect we know that the energy level will be split into two. So that I will explain the Zeeman effect in the next video. So for now you just know that in Zeeman, if we put an electron in an external magnetic field, so the energy level of the electron split into two, right? So and that energy level splits like this, goes like E is equal to En. En is the energy of the electron without any external magnetic field, so then it will be plus mu b ml for and 2ms into bz or hz in this matter. Now the energy difference is del En plus or minus mu b into bz. This plus and minus comes from the electronic spin ms, because we have the spin quantum number as plus or minus up. So that's how the energy level split. I will explain more in details in my upcoming video how these energy levels split. So suppose we have put an electron in an external magnetic field H naught. Now the electron already splitted into the electron energy levels are splitted into two with this energy gap. Now suppose we have put another frequency dependent magnetic field in the perpendicular direction to the previous external magnetic field. We have so now what will happen if we give the electron the same amount of energy, which is this energy gap, which is, if I put an energy with h mu 1, which is equal to this energy gap of this splitting, so what will happen? So what will happen if the electron is in, let's say, plus half state? If the electron is in plus half state, and if we give the electron this amount of energy, then if this amount of energy matches with the energy gap or the resonance energy gap with the plus, which it takes to go from plus half to minus half, which is take to go from the plus half to minus half state, so then the electron will shift is spin angular momentum to plus half to minus half. If the spin was in up state, the electron was in spin up, then the electron will be in the spin down test of, or we can say if the electron is in plus half state, the electron will go to minus half state. Alright, and the reason we put the external frequency dependent magnetic field in the perpendicular direction, because if we if we put the let's suppose we put the same magnetic field in the same direction or the parallel direction to this previously mentioned magnetic field, then what will happen? Then the amplitude of the magnetic field will increases, and we will get the energy gap of this much bigger. That will not gonna change the electron spin state from plus up to minus up, so that will not gonna help us in the experiment. So that's why we put an perpendicular magnetic field, so the electron spin state can be changed. And mathematically you can visualize this by the torque, the tau, which is mu cross b. If we apply this b in the same direction as mu, then this torque will be 0, and if we apply this mu with this b with the perpendicular direction, then we will get the maximum outcome. So that's why we apply the this h1 magnetic field in the perpendicular direction to the h naught, which is this one. So if the resonance frequency match, we can calculate the g from the slope of mu and this h naught data. How can we do that? If we vary the mu and plot it with the h naught, we'll get a straight line, and from the slope we can calculate this g. Alright, this h naught actually we use a Helmholtz coil whose magnetic field is this, and this is for the steady current I, for the DC current, but we use AC. So for that case this H becomes 2 root 2 Q by P into H. So for AC current we get the peak to peak voltage, which is 2 root 2 into H for the which is P. So we get 2 root 2 into H, which is this, for this P amount of division. This is the signal which we'll see in the oscilloscope. All right, so this 2 to H is the amount of H naught which we will see for P division. So for 1 unit division we get this by P, and we have to get this data. So this is Q and this is Q. So for Q division we get that Q by P into H amount of H naught. All right, so from this we can say that this H naught is dependent of Q. All right, so if we change the frequency of this external magnetic field, the Q changes, and that changes this H naught, and from that we get a straight line, and we can calculate the G from the slope. And but this is a tricky method, because the cavity of the substance is dependent on it varies as lambda by L, so which is dependent with the frequency. So changing the frequency doesn't help us. It doesn't it may some error in calculating G. So the preferable method we use to calculate G is we measure the H naught direct from the oscilloscope and put the value and get the G. So what we will do, we'll vary the current we'll vary this current, and for each current we'll get a different Q, and from there we'll draw this 1 by I versus q versus 1 by I graph. From this slope we can calculate the qi, and from that we can get this h naught, and we can put this h naught value into g and get the g which is expected to, and obviously we'll not get exactly 2, we'll get some 1.98 or something like that. So this is the whole experiment. We can use both the method, but this method is more accurate. Alright, I will put another video about the Zeeman splitting in my next video. Alright, bye then.